Next, please welcome from the Lighting Research Center at RPI, Daniel Frering and Jennifer Brons.
This is mostly going to be a Jennifer Brons show. I'm just going to introduce us. So I just want to tell you a little bit about the Lighting Research Center for those of you who don't know us. That's our mission, advancing the effective use of light. We do work in light and health, which is what Robert was talking about. Human factor, safety, security, technology, energy efficiency, plant growth, outdoor. If lighting touches it, we typically have done some sort of research over the last 30 years or so. We have a 30,000 square foot lab in Troy, New York, which is right near Albany, for those of you who don't know upstate. And we have 34 full-time faculty and staff who do nothing but research, and another 15 or so graduate students in master's and PhD programs in lighting. So that's what we do. What we're going to talk about today are modeling and measurements. So we heard Star talk about illuminance and luminance and all those metrics. We heard Robert talk about circadian entrainment. Now let's put some numbers to that so you can get an idea in a basement apartment how much of this would you expect to get with different window configurations. So when we look at lighting, we always consider, as Robert said, the 24-hour cycle. You can think about the 24-hour day is always 24 hours, but your circadian system is a little bit longer than that. So think about it as your watch running 10 minutes fast. Every morning you'd have to reset it back to the correct time. And if you didn't, you'd be 10 minutes ahead the first day, 20 the second, 30, and so on and so forth. And that really is what we call a lack of circadian entrainment. Your circadian system then is not matching that day. And what is the most robust reset of that is light, light through the eye. And we've come up with a metric that is called CS, or circadian stimulation, circadian stimulus. And it takes into account the things that Robert was saying, the spectrum of the light, the amount of the light, and you have to think about then the timing of the light. You typically want this in the morning so that you can reset that clock, and that's the important time for most people. Now, if you're a shift worker and you work at night in a hospital, then that's different. But for most people who work regular shifts, that's the important thing. So Jen's going to talk about illuminance, which is the amount of light you need to see to do visual tasks, as well as the CS, the circadian stimulus that you get from that light. And those are really the two things that light can do. As Robert said, daylight does it, electric light can do it. You can now, with the use of LEDs and other technology, pretty much model the spectrum of daylight with electric light. Where? Obviously at the eye, that's the important measure for circadian stimulus, and then there are different ideas on how you might do that. But I'll let Jen go through our models to show you what we found.
Good morning, everyone. I'll try not to fall off the stage here. I'm Jennifer Brons, and I'll tell you about some of the models we built for a hypothetical basement. Working with CHPC, we developed a computer model of a hypothetical basement apartment. We ran 8 simulations with various daylighting and electric lighting solutions, so I'll show you those. Our hypothetical bedroom was about 120 square feet, so our window is 12 square feet. We have our 7'6" ceilings and so on and so forth. We have a neighbor 10 foot away, so you'll see the same image of this hypothetical room several times under several conditions. I happen to choose equinox, noontime, on a, say, hypothetical clear day. Sometimes it's sunny in September. So we used commercially available software to run these simulations, primarily daylight and some electric lighting solutions. So I'll show you those results. Simulation A is our base case with our 12 square foot window with clear glass. I'll go into more detail on this one and then kind of do a briefer version on the remaining 7 versions of this room. The window is on the south wall and the ground level is 3 feet above the floor. Our fixture happens to look, the ceiling mounted fixture happens to look black right now because I have it turned off, so we're only looking at the effect of daylight in this space. Let's see, on the next slide, we've got some of the calculation results The left side is what we call a pseudo-color or heat map rendering showing the amount of light landing on the surfaces. I have standardized my maximum level as 500-foot candles. I actually have more than that right next to the window. But you get an idea how the sunlight is landing on the surfaces of the room and interreflecting around in the space using the image on the left. And on the right is a sort of a plan view of light landing on a surface if it were at 30 inches above the floor. Those lines indicate the transition between higher light levels and foot candles and lower ones. So the cyan line, for instance, on the right is showing where 25-foot candles would land in the back of this room on this really sunny noontime spot in this person's bedroom. And the next click shows where that 30-inch line would have been in the room. So for the remaining sites, I'll just show a pseudo-color rendering and a photorealistic rendering of what the room would look like. This is condition B. That's that same window, but with frosted glass. So you're seeing more light bouncing up to the ceiling, to the side walls as a result of this frosted glass. It's kind of like your blizzard condition, blizzards in September. That allows less light into the room than if it were clear glass. So we'll see at the end our summary statistics about light levels. This is actually the lowest light condition, even though it looks bright. As Star was saying, having light bouncing off of walls and having high reflectance surface makes a room look brighter than you might find if you were looking at a light meter. So that's your condition B. Condition C is the smaller version of that just an egress window, half of that height of window. And we're using a reflective light well, such as what we'll learn about from Limitless, from the people from UK will tell us a bit more about how they've solved basement lighting challenges in UK. So this is providing a little less light in the room as if you would have a larger window, but it's still doing a nice job of kicking light up to the ceiling and bringing light into the space. In this case, in condition D, it's the same one window, but we have added some electric lighting in a space where someone is trying to do some work and they don't quite have enough light to stimulate their biology. So we added some electric lighting on the walls. It's actually a lot more than I need. You can optimize. I'll click. I have a CS value of 0.56, and we can tell you more about how this works on a scale of 0 to 0.7. So that's very high light levels, similar to what you'd have outside on a sunny day from this electric flat panel that's surrounding my workstation area. You can actually optimize this by using a smaller light source or fewer of them, something around 50-foot candles of a neutral white light, or even a high color temperature bluish white light, maybe something around what your light meter would say, around 20 or 30-foot candles. Condition E is 2 of those nice windows. It's always nice to have daylight coming from 2 sides of a room. So it's getting you the same amount of glazing area, but on 2 sides of the room. So that looks nice too. And here we are showing an electric lighting strategy with that standard code type window on the south side. On the left side of the image, we have 3 electric panels that are sort of simulating what an artificial window might look like in that space. So that's providing very high light levels in the room, on the ceiling, on the walls, and all around the space. So that we have new technologies available that can really simulate how windows might look in the space without actually punching holes in your walls. In the next slide, I'll show you some examples. You could use a flat white type source. You could create a programmable lighting source and with an artificial window that maybe your tenant could use their smartphone to program to turn on gradually as their alarm clock, or when they are reading late at night, they could change the color temperature. So there's a lot of opportunities now with new lighting technology to program lighting into your artificial windows. You could maybe backlight your stained glass effect, or something that looks like a nature scene, or you could have something animated. So there's many options for creating artificial windows that appeal to psychology and can actually maybe provide enough information for the biological system. Condition G here is that same base case A condition, but with your stereotypical dark paneling on your walls and your ceilings. So this we'll show later how it compares in terms of overall light output and how dark that looks. You can hardly see it on the screen right now, even though it's got the same daylight ingress. So here's the comparison of the pseudo-color renderings. The image on the right shows a lot more green on the walls, whereas the one on the left is just sucking up all that daylight in the space. So you can do a lot by improving the reflectance characteristics of that room. Paint them white. Condition H is that smaller egress type window with an artificial skylight. So there are some new technologies that are coming on the market now that can allow us to cut in something into our ceilings to make it look like we have a skylight in the space. There's a product coming later this year that will have color changing in it to make it look like how Star was showing the color of the light changes throughout the day. And there are photorealistic flat panels. Those are used commonly in medical scenes where people are being wheeled out for MRIs and so forth. They put something interesting in there. But maybe you could do that in your basement apartment as well. Here's a summary of the average light levels across those rooms. We have very high light levels right next to our window on our sunny day. So actually, overall, these are very high light levels. But our highest light level is at the egress window with the artificial, I call it, quote, windows, with the electric lighting on that one side. I think I'm actually going to go back, show you a little more. Excuse me. On average, with the shaft of sun, I've mentioned it's thousands of foot candles, but in the back of the room, it's probably pretty dark in comparison, as Robert was saying, as you get very far from the window. So our lowest light levels was at the frosted base case, that condition B, but in fact, those are pretty high light levels on this sunny day at noontime. But other times of day, of course, you would see it scale accordingly. Now, I've taken that information and applied some of what we've learned from other simulations to calculate changing from light landing in a horizontal plane to light landing in a vertical plane. I would expect in those areas close to the window, I have very high CS values, and enough to be perfectly capable of resetting your biological clock. But as we get to at the back of the room, we consider a target of 0.3 CS to be useful when we do our laboratory and research studies in the field. So some of those areas on the left side of the graph are probably not sufficient light levels to meet our biological needs. Depending on how you arrange the furniture in that room, you might need some electric light sources to meet your biological needs if you're actually in this basement working all day. We did a quick cost comparison, estimating the material costs for some of these solutions. The first few lines are the ones sort of base cases, what you might have already if you're a homeowner of one of these facilities. And we found that the electric lighting solutions are on the 3 to 4 digit price range for ways of bringing light into the space. Quite affordable compared to installing more windows in the space. So if you're really trying to make ends meet, maybe electric lighting solutions could be a way of meeting your biological and visual needs for light in these apartments. Of course, it's beautiful having windows, but so costs are a factor. So overall, we think electric lighting could be a cost-effective solution to meet the biological and visual needs in basement apartments. Light is, for vision, we don't need quite as much as we do for the biological needs. So as Star mentioned, you don't need that much to be able to see your New York Times and so forth. Highlight levels are needed in the morning, particularly. Electrical lighting, we think, can be a pretty cost-effective way to meet those needs. Windows do have other benefits, of course. I'm sure we'll talk more about view to nature and ventilation needs later we'll talk about. And disadvantages, of course, privacy, glare, sound, moisture, heat loss, and gain. So windows have pros and cons that electric lighting doesn't have to struggle as much with. So if illumination is the main goal for these basement apartments, we think that electric lighting can be a cost-effective solution for homeowners and people trying to live in New York City. So thank you for having us. Look forward to a discussion.